Okay, so hello everyone. I'm Nicolas Goeman, second year PhD student at the Crystal Laboratory. I'm supervised by Pierre-Antoine Touvenin and Pierre Chenet. And as Pierre said, I'm gonna talk about something closely related to what he just presented, because I'm presenting an alternative statistical model. So we are still in the main scenario of having an inverse problems we want to solve. So we have access to some observations Y of some interstellar cloud, and what we are interested in is to find back some physical parameters from this interstellar cloud. And here the noise model again is the same, and it is quite complex. We'll come back on that. So again, we're still in a Bayesian framework where we suppose that the parameters, the physical parameters, are random. And so the main quantity of interest here is the posterior distribution. So the distribution of my physical parameters, knowing the observations I have access to. And from Bayes' theorem, we can build it by combining the likelihood distribution, which was the forward sense we had just earlier. And we combine it with some prior distribution about our physical parameters. So some prior knowledge we have and we know about it. Okay, so what specific inverse problem we're dealing with right now? So it's the same as Pierre Palus just presented. So we have our physical parameters here in green, transformed by some forward model encoded by a neural network. And here we have two types of noise, so a multiplicative one and an additive one. Here the forward model can be highly nonlinear, which can induce multimodality potentially in the posterior distribution. And the main problem here is that this mixture of two noises makes that the resulting likelihood from this observation model is not like a standard distribution such as a Gaussian, a log normal, or whatever you want, and therefore you cannot use it easily in whatever inference algorithm you want to use. And on top of that, we also have censorship. If we look at the more formal definition, the censorship is just a maximum operator. And here are some examples of distributions for the two different types of noise. The existing approaches to deal with that kind of observation model are the following ones. So the easy one is to simply neglect one of the source of noise. Then you have simply a Gaussian or a log normal distribution, easy to work with. You can compute the PDF, whatever you want. That's nice. The problem is that it's not very accurate. So it's cheap, but not very accurate. So what Pierre Palus did during his PhD thesis was basically to work on another approximation of the likelihood, a bit more complex, because it basically uses a weight function to put weights in a geometric average in between the two pure approximations. And so this is nice because it's more accurate, but at the same time, it can be difficult to fine-tune this weight function. And it also comes with an intractable normalization constant because of the geometric average. So what we propose instead is to see the same observation model in a slightly different way. So here we can see that we have the same ingredients, the two noises, the forward model, but we have introduced some auxiliary variable here in the darker green, which needs, because it's unknown, we need to also sample it alongside the theta parameters. And what is nice with this new hierarchical approach is that now we have a two-level likelihood distribution where each level is a well-known distribution. So the top line is a censored Gaussian distribution, and the bottom line is simply a log normal distribution. So therefore, we can have a two-stage likelihood distributions for which we have an easy form that we can use inside our inference algorithms. So that's nice. We have access to an exact likelihood distribution that represents the model we are targeting. So, okay, if we compare the two models, we see again, yeah, that we have the same ingredients, and that the U variable was kind of present, but not sampled in the previous example. So that's nice. If we now switch back to the posterior distribution, so how do we build and plug the likelihood distribution we have just seen from the hierarchical approach into the posterior? We can see that we can easily have access to the conditional posterior at the pixel-wise level, I mean. And so we can see that we have our prior distribution, and here we have the product of the two lines of the hierarchical model. We have the product over all lines because one theta n is, of course, interacting with all the lines. If we switch to the full posterior distribution of the whole map, it's simply a matter of adding product over all the pixels. So it's quite straightforward to switch from one to another. Okay, and so the missing part now is the prior distribution to complete the full posterior distribution. And we simply use, again, the same ingredients Pierre just talked about. So we have the special regularization, which is very important with the checkerboard structure. And we also have some validity intervals because we expect our parameters to belong some validity intervals. Okay. So that's nice. We have access to a posterior distribution, which is exact this time. So, okay, that's really nice. The problem with that is that if we look back at the posterior distribution here is that, okay, we can compute the normalized density, use it and use it, but it's not a standard distribution, and therefore what I'm interested with this posterior distribution is to have access to the mean, the variance, or whatever statistic you might want to use. So this is something we do not have access to directly. There is no closed form solution for those statistics. So one way to deal with that problem is that let's say you have access to samples from this posterior distribution, then you can compute estimates of the mean, the variance, whatever you want again. So this is the goal of Monte Carlo methods. It was supposed to have I think it's not working. Okay, so you were supposed to have a super nice MCMC simulation showing that I got samples across my whole distribution. So trust me, it works. But yeah, with Monte Carlo methods, you can have access to samples and therefore derive estimators of your quantities of interest. So the missing part here with the MCMC method is to design what we call the transition kernel. So when you build your sequence sequentially, you need to find a rule and a kernel to switch from one sample to the next one. And so this is the missing part to complete the full new algorithm that will help to converge and draw samples from the exact posterior distribution we have just introduced. So the basic idea behind the sampler is to use what we call Gibbs sampling. So we'll focus on the posterior distribution in a pixel-wise manner using the conditional distributions instead of the whole map. This is still quite fast because of the shape of the likelihood. We can identify groups of independent variables and then use what we call chromatic sampling to sample various pixels in parallel, which makes the whole procedure quite fast. And okay, so this is the main structure of the transition kernel. Now we are just missing the proposal distributions to propose new candidates theta and u, because again we need to sample u alongside theta. And so for the p-mala, what we do is we use again the same ingredients as Pierre Palus used in the previous talk. So a p-mala for a good local exploration. Once I'm in a mode of my posterior distribution, I want to explore it quite efficiently. The other kernel that I'm using is a Gaussian mixture inside a MTM kernel scheme. And it's useful to allow you to switch from one mode to another inside your posterior distribution on the space, I mean. And once we have sampled a candidate theta, then we can propose the candidate U. Here we have a twofold strategy because we have seen that we have a censorship. So in the censored case, observations coming from Y are useless. So basically, you can use what we call ancestral sampling. So using as a proposal distribution, the conditional distribution of U knowing the candidate theta. And in the observed case, we still have this information coming from theta, but we also have information coming from Y. And so what we want to have is to have a proposal distribution as close as possible to the product of these two densities, to have an efficient proposal distribution for U once we have sampled theta. So if we look at that in a more algorithm manner, so we have our chromatic groups, and then this second loop can be done in parallel because all the pixels inside this group are independent of each other, conditionally on the other group. So this is quite, this for loop is quite efficient. Then we first sample theta using the p-mala or the Gaussian mixture, and then we sample the variables U. With the sensor case, we have ancestral sampling, and the observed case, we have used a gamma distribution fitted to match the product of the two densities we have just seen earlier, and we fit the parameters of this gamma using informations from theta and from Y. And finally, to be sure that we converge towards the posterior distribution of interest, we have the classical accept-reject step inside the acceptance ratio of classical, for example, Metropolis Hastings algorithm. And that's what ensures us to converge towards the posterior density. So that's fine. We have our algorithm, we have the statistical model, the exact one. So we can now switch to the results. So for the results, we're working on synthetic astronomical data, yet realistic. And so we have access to 10 maps, 10 observation maps, so 10 spectral lines. We are interested in reconstructing 4 physical parameters. So here the visual extension, for example, and we have maps of a bit more than 4,000 pixels. Here the multiplicative noise is set to around 50% for the example. There is no physical meaning behind it. And we'll compare the approximate approach of Pierre Palus with the new hierarchical approach on various metrics. So first, if we look at the MMSE results, so the MMSE is just the mean of the posterior distribution we can compute thanks to the samples. So on the first line, we have the ground truth parameters for the thermal pressure, the intensity of the radiation field, or the visual extension. And second line, we have the approximate approach, and last line, the hierarchical approach. What can we notice here is that basically both approaches perform quite well. They manage to reconstruct like the physical behaviors of the maps, of the physical parameter maps. They show comparable results. They both struggle on the last parameter, which is known to be difficult to estimate. Okay, and so if we switch, because one of the main motivation of using a Bayesian framework is to have access to uncertainty quantification. And so this is what we can have with, for example, credible interval-based metrics. So we have the credible intervals at 95% for both approaches. Again, we have comparable results, maybe slightly more uncertain for the hierarchical approach, which shows, because we have seen that the mean of the two distributions were maybe kind of similar. Now we are seeing that maybe in terms of the shape of the posterior distribution we are targeting, we can see some differences. So there is That's where we start to see some difference between the two approaches. And finally, one really interesting metric is called the ELPD. So the ELPD is basically a metric that uses your samples that you got from your MCMC chain, and they evaluate it on the likelihood term with new observations that were not used to infer the parameters of interest. So basically, you are just giving the likelihood new observations unseen by when you try to get your samples. And yeah, you evaluate the samples you got from your MCMC sample. Here I'm showing the difference in terms of ELPD of the hierarchical approach versus the ELPD map of the approximate approach. So basically in red, it tells you that the hierarchical approach is doing a better job at like understanding and being reliable with respect to the generative procedure underneath. And in blue, it's the opposite. So the approximate approach is doing a better job. So what can we say here is that as a whole, the hierarchical approach seems to better represent, understand the generative procedure underneath. So let's switch to the conclusion. So we have seen that we have introduced an exact hierarchical model. Exact in the sense that now we have a likelihood distribution which is not approximate, that really target the ingredients we wanted to show in our observation model. So it's treating the additive noise, the multiplicative noise in the way we describe them. We have also introduced an efficient MCMC sampler to sample from the resulting posterior distribution. And we have shown comparable point-wise reconstruction performance. And we have seen differences in terms of predictive performance basically on the new observations. Here, there is also a point about computational overhead because we are now sampling a new variable. So for example, in this example, we were sampling 14 parameters in the hierarchical case compared to 4 in the approximate case. So this computational overhead is quite limited in a sense. And finally, like the main perspective right now is to integrate all this work about the hierarchical approach inside the Beatroots library Pierre just presented, so that any user can use whatever method he wants, the hierarchical approach with maybe a slightly higher computational cost, or switch to approximations such that the interpolation or the pure approximations we have seen at the very beginning. So thank you.
Thank you, Nicolas, for this very nice talk. So is there questions? In line? Jérôme?
Am I correct that the hierarchical approach is better suited for parallelism, or is it the same?
You mean for parallelism, parallel implementation?
Yes.
No, because you might think that because of the comment on the chromatic Gibbs sampling, but it's like the chromatic Gibbs sampling is simply so. For example, when we have seen the likelihood distribution. So the likelihood distribution is completely independent for each pixel, each line of observations. So this is not a problem in terms of parallelization. The only term that brings like special correlation between pixels is the special regularization right here. But the good thing with that special regularization is that like the dependence it introduces is that we have a checkerboard pattern. So all the pixels of the same color on this checkerboard pattern are independent of each other. So when I mentioned the two groups of independent variables, so it was like the two colors here. But this is something that is also possible with the approximate approach. So in terms of parallelism, there is no clear difference.
Okay, on concerning the different algorithms that are in the method, will it be easy to bring them, to port them all on GPUs, or can it be difficult for some of them?
Yeah, that was one of the goals at some point. So the problem with MCMC method is that you have something that is sequential by nature. So like there is still like a kind of a wall where you cannot go beyond the sequential behavior of the MCMC, but there are definitely steps that you can parallelize. For example, here, the MTM scheme, what is done, because here you have a good, an efficient local exploration, and here the price of trying to go from one mode to another is that your proposal distribution is very bad. So basically, it just draws some samples without knowing where. And what is done here is that the MTM method uses not only one sample proposal, one candidate, but like let's say 100 or 50 or whatever you want. So that might be costly. It's already vectorized in the code, but this is a place where you can gain a lot of time and with GPU implementation.